Hi and welcome to this quick answer to this question. So basically this is not, it's more of a completion of an existing answer to the following question. So this user wants more information on how to use this lift drag plugin in Gazebo and more or less a guide on how to use these parameters to make its model move around a fluid. So there's an answer already that states basically to have a look to the documentation. So what I would like to give the community is more of a practical first example, hands-on experience on how to use this. So basically that's it. So let's go. So the first thing is that I'm using ROS Development Studio to make the simulation, but you can do it locally, of course. And I'll go to my project and launch the test that I've already done. Okay, here we have it. So the first thing I'm going to do is select my simulation workspace because that's where I have all my simulations. Here, the Catkin workspace would be where I put my code to use in the simulation, and this one is for my simulations. In your local computer, just your packages, your Catkin workspace. So here, I've done this buoyancy tests because continuing to another question that I answered a few weeks ago about buoyancy and so on. So let's have a look. So the thing I've done is, let me have a look. So I've done this launch, which launches two things: a world, an empty world with some blue walls to simulate the sea. That's it, which is basically the same example as the submarines example in Gazebo tutorials. And then I've spawned this very basic model of a, let's say like a tadpole or a fish, a very simple fish, and we'll make it move through the fluid. And it will move by moving a tail, a very basic one. You'll see in a minute. So basically is those two things. We have the launch file, which is launching a world, ocean world, which is this world here. And if we highlight the syntax, as you can see, it's just some scenes, lights, and some models to simulate blue around. You'll see in a minute. You have this same example in Gazebo, but I'll post all the code that I can in the answer, so don't worry about that. And the important stuff is here. So sphere with fin complete. Here I'm spawning a sphere and with some controllers to move it around. It's basically that. I won't go in depth in here. If you want more, please, if you need more explanation, please leave it in the comments below. But basically we're spawning a model, a URDF model that it's called sphere, floating sphere with a fin. So let's have a look. Here we go, floating sphere. Okay. There we go. So we have this model. So we have this model here that it's made of two links, a sphere of radius 0.12 and a cylinder of these dimensions. They weigh, so this one is really tiny and this one weighs a bit more. Why do they have these weights? Well, these weights are made for buoyancy purposes, which I'll explain in a second. But basically we have two links, okay? And then we have a transmission that makes it move around in this joint. And then we have the plugin itself, which is the most important part here. Okay, so let's dig in. So I'm going to launch it, and you'll see more in a minute. Let me see. There we go. So I launch it. There we have it. So as you can see, it's very simple. It's a sphere with a cylinder that makes the function of a fin. Okay, we have it paused for the moment, just to show you. So if we go to the code again, we can see that the joint, this one, will make this fin move up and down. Okay. But the thing that interests us the most is all these variables that we have here. So we are going to talk about them. So here we have this line here talks about the fluid in which you are, basically, and all the variables that you need to define how this fluid works and behaves. This is one. Then we have the area that will calculate what effect has in the fluid. So more area, you'll have more lift, more drag, and so on. This, I'll tell you in a second how to calculate all this, but then we have the upward and the forward vectors, and then we have the link, which is referred to. In this case is the sphere caudal fin link, which is this one here, which is the cylinder, the purple cylinder here. Oh, green, sorry. Now I have it green. There you go. So just because I didn't change this, I'm going to change this in a second. There we go. This is just for RViz purposes, but so here we have, that's why it's green. There we go, the link. So what's these values? So if you go to the documentation, it's quite well explained, and essentially what we have is we have our fin here. Let's have it side by side so we have our fin, which will be the element that moves the robot around. Okay, so if the fin is totally like this, it won't do any drag, it won't give any force whatsoever. Okay, if you change the angle, it will give a lift when it moves. So the lift is generated when some fluid goes around here and through there, then it will generate lift. So you would need some kind of propeller to move it around. Okay? But the same thing applies more or less to the drag. So basically, if you change the angle, you'll have more lift, and there's an angle here, which is the maximum angle, the attack angle, which gives you the maximum lift force. When you continue and you go up and do it bigger, the angle, you'll start losing lift. Why? Because there's cavitation, another fluid stuff, which we won't talk about here. The thing is, you have this graph that behaves more or less like this. Okay, so in Gazebo, in this plugin, this is simplified by two lines. Just this one, this section, and this section. And we have to define the angle of this line and this one. That's it. This is what we are defining. And this is what here, all these variables, all these parameters are defined. So in this case, we are giving an air density of 1,000. So let's say water, 1,000 kilograms per meter cube. Then we have the CLA and the CDA. What are these coefficients? So these coefficients are talking, if you go here, you see that you have the CLA and then you have the CLA stall. This talks about the coefficient of this line or the coefficient of this line. And it exists for the lift and for the drag. We're going here. If you go down here, you'll see that you have the CLA and the CDA. The CLA talks about the lift. So all the things that have to do with lift. So if you get this robot to move around, this will generate a lift if it has a certain angle. Okay? So if the robot moves in this direction, it won't generate any lift. But if we change the angle of this fin here, then it will generate the lift. Okay? Because the angle between that direction of movement and that fin, it's different from 0. So it will generate some lift, depending on the definitions that we stated here and that we stated around here. Okay, in the CLA. This is the lift. So we have the CLA, which is before the maximum attack angle, and then we have the CDA, which is the CLA stall, which is after. If we go again here, so before and after. Yeah, understood from here. So in drag happens the exact same thing. We have one before and one after. So the question is, why here you have 0 lift and some drift? Well, because in this case, we are not generating a plane. We're generating a fish. And we're generating a propeller that moves through drag, through friction. It doesn't move through lift, but through friction that will move this sphere forwards and a bit up and down. That's why in our case we stated here 0, because we don't want a lift. We don't want that this fin generates some lift when it start moving, okay? In reality, you'll have both. Sometimes, depending on what application, you may have both, because you have lift when you start moving and you have drag also, okay? So depending on what, and then talking about alpha stall and A0 are just parameters that you can tune to change the starting point of the angle and so on. So in this case, we don't need it because we just want it perfectly 0 when we start and at this configuration. But depending on what you want, you'll have to change it. Okay? So once you have that, then you have the area. The area, it's calculated through, so the area is the area of the link, of the model of the link, the collision element. In this case, sphere cutoff fin link, which is here. And if we go to collision, we have a cylinder. So we have to calculate the area of a cylinder. Okay, so you have to calculate. I have a script here, which I'll post, which I used for buoyancy. And if we go here, if we go here, calculate cylinder area, you see the formula. So we need the radius and we need the height, and with that we have the area, and that's the area that I stated exactly here. Okay, that's it. There's no mystery about that. Then we have upwards and forwards, which is quite interesting. So if we go here again, you see that the forwards and upwards vectors are basically defining how our wing or our fin is situated and how it will work. So in our case, we just wanted to go upwards in the x axis of always of the sphere caudal fin link. It's referred to that. And forwards just in the x direction. We'll see it in a minute in RViz. I think it's better that way. And then finally, this is a bit tricky because we are stating here where the center of pressure is. This means you have a picture here, which is you have this plane here, and you're saying, okay, the force will be applied in this point. So here, in our case, we are saying, okay, I'm going to put the pressure in the tip. Why? Just to maximize the force that we apply, but we could do it here or we could do it here. It's basically you have to decide a place where it's physically coherent and the robot moves as it should, as you intend to. So in this case, we stated that it's here because it's a distance from here, sphere to here. Let's see. So the radius of the sphere is, there we go, 0.12. So it's 0.12 plus 0.7 by 2 because we are going to go all the way there. So if you sum up that, you'll get this point. Okay? And it's negative because it's contrary to the axis. Okay? So I'm going to move this around to see what happens and show you some stuff. Okay. Then I'm going to open the graphical interface. I'm going to remove what I had here, and I select my controller. In this case, I only have one. Plus, let's put this, okay. I put sine divided by, I don't know, 100, for example. This will issue through this topic a sine wave. So it will move more or less alternatively and will move the fin as it should. So now I publish, and now I play, and there we go. Whoops. There we go. So as you can see, it's moving forwards through drag. Through friction, there's no external forces of any kind except what you would have in physics through drags and lifts and so on. And there you have it. If you stop it, it just stops. Then we can put it back again. Then, of course, because there's no any kind of guidance in this very simple robot, it just drifts more or less around, but you get the idea. This is just apply it to your robots and tweak stuff so that it works as you want it to work. Okay, so just a tiny little thing. So if we launch RViz. This is to explain the upper and forward. So RViz. Let me upload. There we have it. Okay, there we have it. So as you can see, we have two axes. We have the basic sphere axis, and we have the axis of the fin. So here you can see how we apply the drift and how the axes are situated to see, okay, here's the forwards, here's the backwards, and how it works. So basically, it's what I wanted to say here. And I hope this was useful. I hope you learned something about this. If you want more tutorials, more in depth on how to use this and do more complex stuff, please leave it in the comments below. And yeah, that's it. So thank you, and subscribe if you liked it, and see you soon. Bye.